Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing with looking at the textbook by Turton et al. For process design. And in this lesson, we're looking at Chapter 2, which is the structure and synthesis of process flow diagrams. And the point is that we are going to have to make a lot of decisions as we go through the process design process. The authors recommend this hierarchy, which I think is very sound. So first they say you need to make a decision whether or not the process is going to be batch or continuous. You need to figure out what's going to come in, what do you want to come out. You need to identify and define what your recycle structure will be. And then the general structure of the separation system. And then kind of the last thing, once you've got the design kind of set, then start thinking about heat exchanger networks or energy recovery systems that you might use. So the first question is, should it be batch or continuous? So in a batch, you're going to have a certain amount of material that you process all at one time over a period of, so many hours or a day. In a continuous process, the feed is going to be sent continuously through a series of pieces of equipment. Now, you can have things that are sort of a combination of these, where part of it is batch, but it goes through continuous steps. Most industrial scale processes are going to be continuous, but bioprocesses and food processes are typically going to be batch. And so we need to, make decisions on this. So some of the things you should consider is if you're not processing a lot of material, probably batch is going to be a better choice. If you have a lot of material, then a continuous process will probably save time and money. Batch accountability and product quality. So if you're doing foods and drugs, you need to have these things FDA certified. And so you need to have those done with batches so that you can clearly identify that this material that was done on this date at this time is going to be off spec, needs to be brought back to the facility to be reprocessed or needs to be tossed, whatever. But that's going to be really important. In terms of flexibility, continuous processes have some flexibility to them in how much you can process, or can you add an extra stream, and maybe you're making ice cream and you want to add some chocolate into it. And so you can do a little bit of that sort of thing, but you don't have a lot of flexibility. The maximum flexibility is going to be with batch processing. Then if you're going to have a lot of different, sort of related to this other one, is if you have a lot of different but similar, so like let's say you're making cookies, okay, and you want to make some with chocolate chips and some with chocolate chips and pecans and some with M&Ms and chocolate chips. They're similar, but they are a little bit different, and so batch is probably going to be easier for you to make those modifications. And then the processing efficiency. Usually this is going to be best if you do this for continuous processes, because you can have separations and recycles that once you get them operating properly, you just, set it and forget it, as the old commercials used to say. So operationally, those are going to be better. You usually are going to have a better chance at minimizing your energy use if you're doing a continuous process. So that's going to probably be a reason for using continuous, which is what is typically done in industry. Now, maintenance and operating labor, that's also going to be better to do continuous, because in batches, you're having to have people actually maneuver the material between batches. You're going to have to clean and just lots of extra labor that happens with batch processing. Now, another reason you might choose a batch over continuous is because of limited feedstock availability. Perhaps you have something that is only available a certain time of the year. Okay? Well, in that case, you're not going to process it all year, because it would be silly to store the grapes for a year and process them instead of just doing it all at once when they're fresh, right? And then product demand, again, sort of like the feedstock availability. If you have something that's only going to be purchased in the winter, why are you going to manufacture it year-round? And then rate of reaction to produce products. When you have slow reactions that have long residence times, a batch operation really might be best because the size of a continuous reactor gets to be pretty large. But if it's a fast reaction, then a continuous process is probably best. Now, most of these batch came up as kind of the better answer, but economics usually drives us towards continuous processes unless I need to do batch. Few last little things here. Equipment fouling, if it's going to have to be cleaned frequently, you may as well do batch because you're going to be messing with it and cleaning it all the time anyway. For safety, continuous processes are going to be better because there's less chance for someone to make a mistake if it's all operated by the equipment. And then controllability, similarly, a continuous process is going to be easier to control. There may be some less than stellar moments when you first start up a plant, but over a short period of time, you get those ironed out. And then it's very rare to have some sort of excursion except for due to malfunctions, or usually it's some sort of operator error, etc. So operator training and scheduling are really critical when doing batch process control. So therefore we avoid that if possible. Step 2 is to look at the input and the output structure. So this is like the world's most simple block diagram. So you bring in certain feed and you're going to bring out certain products. We're going to bring in the feed from the left. We're going to bring the products out on the right. And then inside is going to happen some reactions. Now don't worry about how the reaction is going to happen or how you're going to separate it. Just envision that it is possible to have these reactions happen and all get separated into perfect little product streams. Now you need to find a reaction set that will do that. And when you list your products, be sure that you include all those unwanted products, all the side products. And then start really thinking about how you could accomplish this. Okay, so you're going to need to do some preliminary material balances. How much feed do you need in order to make so much product? Do you need any extra chemicals in order to make this work? Do you need catalysts for the reactions? Are there solvents that are going to be required in order to do the separations? So go ahead and think through those things, and as you realize you're going to need something, add those to your feed or to your product. And then create a block flow diagram. Now this is more than what we did just a moment ago. Typically, you bring the material in, you prepare it so you get it to the right temperature and pressure, the right combination of ingredients. You send them to a reactor, they make your product. And then you're going to separate these things. And the separation then is going to create products. You may need to go to a second reactor and second separation. You may just be able to take your waste products and send them back to recycle and send your products and any byproducts that are sellable onto storage tanks. And so you can go through and start creating what these blocks are going to be. And typically this is sort of the basic scenario that you need. You also want to think about what your feed purities are and if there are any trace components. So let's just talk about, for instance, ethanol. If you are using ethanol that is pure ethanol, well, then you've got to have some special licenses for that. But if that's your feedstock, but usually ethanol is either going to be diluted because it's got that azeotrope, or it's going to have some sort of poison added to it so that it isn't drinkable? Well, you're going to have impurities. So some impurities are unavoidable, and some are there and you just buy it with that impurity and you deal with it. Some of them don't interfere with the reaction and some do. So if you have impurities, you need to make a decision on whether you want to separate it out at the beginning or wait until after the reactor and do it with all the rest of the separation steps. Okay? If it's going to poison my catalyst, or if it's going to cause side reactions that make some unfortunate byproducts, then I want to purify that impurity before I send it to the reactor. But I may, again, choose to save it till the end because it might save me a few steps of separations. You might need to add some extra things to the feed. Perhaps it's not going to be stable except for in the presence of a typical one. Maybe you need to add maybe a nitrogen to inert the system so you don't accidentally introduce oxygen, something like that. So you may have some additional feeds that you need to stabilize the products, or if you're doing separations, maybe you're needing to add a solvent. If you are adding inert feed material, sometimes you're doing that for stability, but you also may be doing it because it's a way of controlling an exothermic reactor. And then you also can do it to control equilibrium reactions. Sometimes that'll drive you to a more favorable equilibrium. So you have your basic block flow diagram, and then you start thinking about replacing each one of those blocks with actual equipment. And at that point, it becomes a process flow diagram. At every step along this way, perform a basic economic analysis and see if this is possibly profitable. If it's not going to be profitable, then just stop. Don't go further. Okay? Also, make sure that your reactions that you've planned on having are actually possible, and do a good literature research survey to check and see if there are any side reactions that maybe you had missed. Step 3 then says look at the recycle structure. So you're going to have a certain single pass conversion across the reactor. So you bring some material in, it reacts, some of it doesn't, and that gets you a single pass conversion. We're going to take some of the raw materials and recycle them back if I can separate them out. And then that, when I look at the overall plant, I get an overall conversion that should be very, very high. Now my single pass conversion may not be all that high. But overall conversion, I typically want that to be, 99% or better. We also then have yield. Yield, remember, is more about when I have a product and side products that I'm making enough of the desired product. A lot of times things like just changing the temperature of the reactor or something like that can change the yield of my desired product. Some of the things you can do to recycle your unreacted raw material, you can separate and purify the unreacted feed from the product and then recycle it. But you need to be sure that that's economically feasible. If it would be cheaper to just, move the stuff on, then maybe that's your better choice. You could recycle feed and product together and then have a purge stream. If you're sending everything back through the reactor, you're going to have a purge stream to get rid of, so you don't overfill your reactor at some point. And then you can recycle the feed and product together, working with your separations, and have that kind of internal to the system. If you are recycling your feed and product together, there's an example in the book, the hydrodealkylation process. In this one, methane is primarily an inert that they are adding to this. Okay, it doesn't react with the toluene. It will react a little bit with the benzene. If the reactant and the product don't react further, then you need a purge stream. if they will eventually react, then you can just keep recycling them. Some other issues you want to consider. If you have a single pass conversion less than 99%, you want to have a recycle stream in there unless your raw material is something that you don't mind throwing away. You need to look at how excess reactant affects the recycle and how it affects your reactor. So look at those. You need to determine how many reactors you're going to require. So this is part of whether you're using a tank reactor or a plug flow type reactor. On tank reactors, you can use multiple reactors, but also you may have one that operates at a certain temperature and pressure and another one at a different temperature and pressure to get you past some, maybe equilibrium challenge, or you're changing catalysts between various things that might happen. You might add an ingredient. So you might need more than just a single reaction to control. So you're looking at equilibrium, you're looking at temperature, you're looking at concentrations, and you're looking at optimizing the production of intermediates in a chain reaction. You also want to consider, do unreacted raw material streams need to be purified before recycling? Do you need to recycle an inert? Can you recycle an unwanted product or have an inert shift the reaction to produce less of an unwanted product? So will recycle help me eliminate an unwanted product? Would recycling an unwanted product or an inert control the reactor operation? Would that help or does it hurt? And then what phase is the recycle? Generally, liquids are easier to transport, okay? But if you are cooling a stream, it does require refrigeration. Interesting spelling there, sorry about that. And that's going to introduce another material, additional costs. So maybe you don't want to do that. So are you going to be able to recycle that product easily? Now, we did talk just briefly that you may need to refrigerate something so that you can get the temperatures right. Selecting refrigerants, we'll talk about this more later, but this is a table here that shows you sort of typical choices that we make for refrigerants, depending on what operating temperature I'm trying to achieve. And again, we'll talk about this more later. So I've got my block flow diagram converted over to a process flow diagram that includes a recycle. Next, I want to look more seriously at the separations. Now, we're going to do a lot more on this, especially when we get to chapter 12. Then we're going to look at whether or not I can do anything to optimize my energy usage. Again, we're going to talk more about this when we get to chapter 15. So both of these are very important, but those are big steps, kind of a little beyond what we're ready for today. Now, you may be wondering, how on earth do you even get started on something like this? Well, one good thing to do is look and see what is being done. So you can look in something like Shreve's Chemical Process Industries handbook. You can look at the Refinery Process Handbook, the Gas Processing Handbook. A lot of these, Kirk Othmer is a great one. And these are going to give you processes that are sort of historical, what people have been doing. But you also can use our library resources to do a literature search and get information on maybe some more current technologies that are being used. Or maybe with a new catalyst, you can get a more specialized reaction scheme. So again, these are more choices of places you can look. I do find that doing a literature search through the library usually is pretty good. I would highly recommend that you make sure you know how to do that. So this is going to conclude this lesson, and I will see you in class. Thank you very much for your time.